questions on the homework. If not, we can just push that back to Monday because our test is on Wednesday. Give you some time to look at it again over the weekend. But getting through chapter 2 is probably the best course of action at this point. So we're going to do 2.6 now, which is called exact equations and integrating factors. Our emphasis will be on exact equations. The integrating factors part of this chapter is not really in our syllabus. I might show you an example with one, but it's not going to be a focus and it won't be on a final. So, but I'll just mention it just so you know about it. But exact equations is the kind of equations that we're going to be dealing with in this section for the most part. Here's a challenge. Solve X. You see that on a test, what do you do?
Is it separable?
Is it separable? First question you ask, is it separable?
No.
No, because that one messes up separability. Okay, what's the next thing you try to think? Is homogeneous, right? You skipped over linear because you saw the y squared here. It's definitely not linear. Okay, so is it homogeneous?
No.
No. Again, the 1 would mess that up, right? If you replace all x's with kx's and y's with ky's, you wouldn't be able to factor a k out of this and to get everything back the same. So that would mess that up. So it's not separable, it's not linear, it's not homogeneous. That's everything we know how to do at this point. It turns out to be another kind of equation called an exact equation. And before I sort of get into what that is, I thought we would sort of work backwards. Consider. Especially if you're a math major, that is one of the most terrifying words you will ever read. Because it usually means it follows, a fact follows that you're like, where did you get that from? And then they're going to work something out, and then... Okay, so consider this function. So I'm just going to throw this function out there at the moment. Right? Just, you know, because I can. Right? Note, and note the following. If I take the partial with respect to x of this function, what do I get? I get xy squared plus x plus 1. What if I took the partial with respect to y of this function? You get x squared y. Do you notice anything? It's the guys over here, right? This is that guy that's attached to the dx. This is that guy that's attached to the dy, right? So our ODE can be written as, I could actually rewrite this ODE as a partial with respect to x of this function psi. This is the Greek letter psi. Capital uppercase psi. It's the standard letter that your book calls it.
Where did you get this?
Yeah.
Consider, okay? Consider this function. It has these properties, all right?
Yeah, but then
Just don't worry about it for now. Just consider it, okay? So I could actually write this function as this guy dx plus right? Or in other words, I could write it as gamma x plus gamma y dy dx equals 0. And for those of you who remember Calc 3, what is this actually? So guess you guys don't remember Calc 3.
We're not going back.
It's the first derivative of the multivariable function using the chain rule. Remember that thing where you did that tree branch? If you actually have a multivariable function, find the derivative of x, the chain rule will tell you that's how you'd have to do it. Okay. So in other words, that's what you have. So you have the derivative of some function equals 0, which means I can integrate both sides, and I get gamma equals what? Antiderivative of 0.
Yeah. 0.
No.
Crap.
What's the antiderivative of 0?
Some constant.
A constant, right? You differentiate a constant, you
So
get
close.
0. Right? So for some constant. In other words, we have this. X squared y squared over 2 plus x squared over 2 plus x equals some constant. Now it turns out, if this relationship is true, then this relationship will be true, because I just showed you it is. Right? It's just undoing the chain rule to get back to here. And so this is actually a solution to the ODE. Okay, and that's exact equation, so everyone understands how to do it now. Not really. Right, so I'm just showing you that if we can find a function that has these properties, right? So if you're given a differential equation, it's not separable, it's not linear, it's not homogeneous, you don't know what to do, but you can figure out, oh, there's this function somewhere out there where if I take the partial with respect to x, I can put it in this position, and I can take the partial with respect to y, and put it in that position, then that function equals a constant is actually the solution to my differential equation. So, the obvious question is,
How do you find that?
how do you find that function, and how do we even know one exists? How do we even know to look for it in the first place? Maybe it didn't even exist in the first place, that we can do this, right? How do you know that every set of differential equations will have some function out there where the partial with respect to x gives you this part and the partial with respect to y gives you that part? So that's what we're going to deal with now. So we're going to talk about how to know when such a function exists, and then we're going to talk about how to actually find it, given that we know it exists. Right? So, let's answer that question first. How do we know that this can happen, right? So we know that we can check for separable, we can check if something is linear, we know how to check if it's homogeneous. How do we know how to check if something is an exact equation, right? So, I'm just going to use a notation from the book. Right? Suppose you have this function. The book calls the guy that's attached to dx, it calls it the function m of xy. The guy attached to dy, the book calls it n of xy. You might see different letters in different texts, but in our text, this is the notation. Right? So suppose we have this, and there is gamma such that the partial with respect to x equals m, and the partial with respect to y equals n. Then what we can do, and assume we have, I have to just throw this in there because it would technically be wrong if I didn't. We have continuous partial derivatives in a region now I'm sort of packing a lot into the sentence, but I have to sort of say it. By region, specifically, I mean a simply connected open set. In this class, we don't really care much about that. And you can pretty much assume that whenever something like this happens, you have this requirement fulfilled in the background. If you do 392, they'll talk about it a little more. But in 391, we don't care about it too much. you know, because this is sort of an engineering math class, we don't care about it. And 392 also, they'll mention it, but they won't care about it too much there either, because it's an engineering math class. If we were math majors, though, verifying that we have this it would be the first thing that we do, because we like to be cautious. We need to actually make sure that our functions make sense where we are defining them. And I do not have an eraser, so I brought my own. Okay, so let's pretend that this happens. How do we know it will happen? Well, notes. What if I take the partial of m with respect to y? What would I get? In terms of psi. Psi xy, right? And what if I take the partial of n with respect to x? What do I get? Psi yx. Now, given that our partial derivatives are continuous, what does this mean? They have to be the same, but, and you would have remembered this by, I always forget how to spell his name, Clairaut's theorem back in Calc 3. It says once your partial derivatives are continuous, it doesn't matter what order you take them in. So gamma xy is equal to gamma yx. But this guy is my, this guy is nx. So if the partial of m with respect to y is equal to the partial of n with respect to x, then gamma exists. We'll be able to reverse the process and find a function that does this. Right? So all we have to do is make sure the second order partials match up, and it would mean that there's some function 2 steps back that gave us both m and n. Right? So all you have to do is, if you have a differential equation that looks like that, m dx plus n dy, if you check the partial with respect to y of the m component, and it's equal to the partial with respect to x of the n component, it means there is such a function that will solve this differential equation in the manner that I did before. Right? So that's the important fact, right? So you look at a question, right? You say, is it separable? Not separable. Is it linear? It's not linear. Is it homogeneous? Not homogeneous. If you can write it in that form and this thing happens, then it means it's an exact equation. And you can find the function psi that solves this equation. The ODE is, let me call it a name. Call it equation 1. So I have an equation in that form. If I do this check, and these are equal, it means I can find such a function, and that function equals a constant, solves the differential equation. And equations for which this happened are called exact equations. So now the question stands, okay, I know how to tell if it exists, how do we find it? There are a couple methods that are really popular. The first method I'll go over is the one in your textbook. And then I'll show you another method that I prefer because it's usually quicker. And did anyone else take 392 here before? Does this remind you of anything? No? Okay, well, it should. You guys remember conservative vector fields? Where you had that gradient function equals the vector field and you had to It's pretty much exactly the same thing. It's pretty much the same thing. Exactly what you would do there is what you're going to do here.
Pretty much talking
So,
about-
if you don't take 392, don't worry about it. When you get there, you're going to know what I'm talking about. Which, by the way, is one of the reasons why exact equations are also called conservative differential forms. That's another name for them, because they make conservative vector fields, which means they conserve work, right, to move from one point. Never mind, you guys don't remember 392 anyway. All right, method one.
We've never been.
Right, so this has a lot of physics applications as well. If you're talking about work, moving work from in a vector field, functions that do this will conserve work. Anyway, okay, method one. Start with either m or n. Then integrate, match up, differentiate, etc. until you go through all partials. I'm going to write this down more concise. So basically, I can just, here we only have to worry about two partial derivatives. In 392, you'd have to worry about three or more. But basically what you're going to do is you're going to start with one of the guys, like partial with respect to x, which is the m. You're going to get to gamma by integrating, of course, with respect to x. Then you're going to differentiate with respect to y. Then you're going to integrate with respect to y. Right? You're going to go through all the partials, right? Start with the partial x, go back to the function, go to the partial y, go back to the function. If there was a third one, go to partial x, back to the function. Partial w, back to the function. Right? You just go through all the partials, sort of cycle through them. And at each stage, when you do something, you're going to sort of match it up with the original equation and sort of figure out the pieces as you go along. Right? Or you can start with y, integrate with respect to y to get here, differentiate with respect to x, match it up to n, then come back to this guy. Might be confusing, but we're actually going to do an example. Let me actually do the same example so you can see where that function came from. Okay, let's do method one with this guy. Okay. So first, I have to check, is this an exact equation, right? Remember, this is your m, this is your n. So you check my, and you check next. Partial with respect to y of this is? Partial with respect to y of this is? 2xy. There's nothing, right? Partial with respect to x of this is 2xy, right? They're the same function. So, they are exact. Right? Which means the function exists. How do we find it? Well, start with one of them. We know that gamma of x is going to be which one? What's gamma of x?
Exact.
xy squared plus x plus 1, right? This means that if I want to get to gamma, this is just the antiderivative of that function with respect to x, which is antiderivative of this with respect to x.
So do we consider any one of the components as?
I can start with any one I feel. X squared y squared over 2 plus
X squared,
x squared over 2 plus
x,
x
plus c.
plus there's going to be a constant. But remember, we have a multivariable function here. Our constant can actually be a function of y. Right? So if there was anything with purely y's in it, that would go to 0 as well. So we consider that a function of y. Right? So we do that. Now, we were at gamma x, we went to gamma, now we want to go back to gamma y. So we're going to take the partial with respect to y of this, and what do I get? Partial with respect to y,
xy cubed
x squared y plus g prime of y, right? Whatever the derivative of this function is, I don't know. Now, what I know about this function, this has to be equal to the n, right? Because remember, this guy's gamma x, this guy's gamma y. So I match this up. This must be equal to yx squared, right? Which is the n. But what does that mean? So subtract this from both sides. That means g prime of y is actually 0, which means that g of y is actually a constant. So I go back to my gamma, my psi. I just kept saying gamma. And we have x squared, y squared over 2 plus. Now my g is just a constant. Right? So I just went back here. Yes?
Explain that again.
Which part?
Just
This last part?
After where it says exact. After that.
Mm-hmm.
Yeah, can you explain that again?
I start with one of the components. Right? Any one I want. Right? So I start with this one. Right? That one, remember, is gamma x. Right? There's this function I'm searching for where when I take its partial with respect to x, I get this. When I take its partial with respect to y, I get that. So I start with this one, which is the partial with respect to x. Now remember, I want to find the function. Right? So if I want to get to the function and I have the partial with respect to x, what do? I integrate with respect to x. That gave me this. Right? But because the function is multivariable, it means if I had y's, they would have died, right? So my constant I think of as a function of y, right? So now, I know this is my function, but I don't know what the g of y is. I have to figure that guy out. So what I do is I differentiate with respect to y, right? Differentiate with respect to y gives me this. However, remember, I know that the function I'm looking for is derivative with respect to y, is this guy. So it means I can set this equal to that guy. When I did that, I can solve for g prime. Once I have g prime, I can solve for g. Right? So once I found g, I go back here and I plug him in. But in this case, the g was just a constant. Right? So the solution is just x squared y squared over 2. Plus x squared over 2 plus x equals a constant. I can bring this constant to the other side. We'll do a few more examples. It's sort of weird to catch on to it first, but once you catch on to it, trust me, it's going to be easy. Some people chuckling like they don't believe me. Seriously, it's going to be. On a final, you're gonna you see an exact square, you're yes! It's gonna be one of the easiest questions, trust me. Yeah. Okay. Let's try method 2. And method 2 is nicer, which when I did 391, it was never taught to me because they just went away in the book. And I never actually took 392. I studied that on my own. One summer I just read the book because I was bored. But Stewart's also gave us that method to do it, and it's like, okay, so I just thought, it was easy when I was doing it, so I didn't mind. It's after I took those classes I found this method. I don't remember where exactly. I know I didn't reread it.
So you read
I
that
probably
book?
what? I was bored.
Oh, you read math looks for fun. I mean, normal people will probably learn the guitar, learn to drive, normal stuff.
This just involves integrating the parts. Basically, I know that gamma is the integral of gamma x with respect to x, and I also know that psi is integral of psi x, psi y with respect to y, right? That makes sense. So all I have to do is just go through all the integrals and figure out all the pieces as I pick them up. So let's do that method. that's that method. So in this case, maybe I should rewrite it. So in this case, it means that my psi is actually equal to the integral of this with respect to x, which is x squared y squared over 2 plus x squared over 2 plus x plus some constant of y. Also, gamma is the integral of this one with respect to y, which is x squared y squared over 2 plus some constant of x. And then that's going to be your answer. Any function that shows up at least once, you write it down in a sum, and that's it. So here's a function that shows up. This function shows up. This function shows up. This function already show up. I don't have to repeat it. That's it. Right? Just integrate the pieces. And any function that shows up at least once, just write it in a sum. That's your psi. Right? You can sort of ignore the constants, because the constant that this guy missed will show up down here, and the constant that this guy missed will show up there. So you can sort of just ignore the constants, pick out all the functions that show up, write them in a sum. That's your answer. So, unless anyone insists otherwise, I will do method 2 from now on. Because it's the method I prefer. Now I remember, I was walking past a math class. And it was over, right? But the professor started erasing stuff, and he didn't erase everything. And I saw this part on a part of this on the board. I probably saw this. And I was like, oh, that works. Oh, yeah, that should make sense. I went around and I played with it. Oh yeah, that works. But I'm sure it's in a book somewhere. Like, I don't think that professor invented it. Let's do some more examples. Yes.
For the last one, you just added them up.
Yeah. Any function that showed up at least once, I added them up.
So you did not add them, like you just wrote them once? Because,
Yeah.
oh,
Yeah, like this guy showed up twice, only write him down one time. Okay, there's no point around
So
it.
Professor, I just basically take the part before dx and integrate it with respect to x, and the part before dy.
Integrate respect to y. Yeah, and write down all the functions you see.
It's gonna always be there.
It will always be like that.
And g of y is always going to be c? Well,
No, g of y won't always be c. But the thing is, g of y will show up down here. Because he would be a function of y, which when I took the part with respect to y, he'd still be here. Right? So the guy that I miss here will show up here. Any guy that I miss here will show up there. The fact that g prime was 0 is why no other function showed up. But if you went to the other method, it's possible to get g of y equals something else. I have to integrate to figure him out. But he would show up in this line, in either case. So,
is that just a line of a constant?
that should be ln of x, I think. Right. And of course, the 2 is not included, or I would have put brackets around. So you look at this, it's not separable because of that 2. It's not homogeneous because of that 2. It's obviously not linear because it has ln. It's actually kind of weird. We could write it as a linear if I want, but those functions are nasty. Right? It is actually linear. But let's do it in exact equation. So who's the m? The guy in front of the dx, right? Now, be careful with this. They could switch it on you. It doesn't change. Whoever's with the dx is the n, right? Don't mix that up. Right? Whoever's ever with the dy, that's the n. So what do we have to check? Check my next. Is partial with respect to y of this function?
1 over x.
1 over x. Partial with respect to x of this function?
1 over x.
1 over x. It means we're exact. It means there exists a function psi that does this. How do I find it? Well, I would know that that function is the integral of this guy with respect to x, which is what? Integrate this with respect to x.
Y ln of x
Y ln of x, right? Because we know our calc 2.
plus 3x squared plus gy.
Plus some constant. Also, this is also equal to the integral of ln x minus 2 dy. And your x is greater than 0, so the absolute values, you don't really need them. You can actually drop them if you'd like, because your x is positive. And so the integral of this with respect to y is y ln x minus 2y plus some constant of x. This means the solution is what? Minus 2y equals constant. And you can check that. Partial of this with respect to x, it's always good to double check yourself. Take the partial of this with respect to x, you should get the function here. Take the partial with respect to y, you should get the function there. But that's it. So obviously, we need to remember our calc 2, we're going to be taking integrals. So you have to remember how to integrate various things.
So there's always going to be a constant?
There will always be blah equals a constant, yes. The solution has to be that. You'll usually get implicit solutions with this method. You can solve for this, in this case you can solve for this explicitly, it's not that hard, but you won't always be able to do that. Your textbook would likely just give you the answer in this form. Let's do another example.
Is there dx?
No, this is how it's given.
I give up. I don't know how to do it.
Give it a try.
I looked at it. I don't recognize nothing. So I'm like, yeah.
Yeah. Problem is, it's not separable. It's not linear. You have sine y and cosine y. It's not homogeneous because you have sine y and cosine y.
It's exact.
Yeah, because we're in 2.6. Yeah. How do we know it's exact?
For the y prime, can we put dy dx and then somehow?
Right. Like this, I would just replace with dy dx, right? Which means I can multiply both sides by dx. If I attach that y prime to the right. Okay, now what? Now what? Yeah? Okay, so we want to check my and next. Who's the m?
The m.
And it's that
Y,
one.
e to the
It
x.
is this one, right? Just because it's in the second position doesn't matter. Whoever attaches to the dx, that's the n, right? So this is the m, that's the n, the way the question proved. Okay, so now I take the partial of this with respect to y, what do I get?
E to the x.
Plus cosine y, take the partial with respect to x of this, partial with respect to x of e to the x, plus cosine y. Ah, they're exact. So, it means my function psi exists. How do I find it? Okay, which one? You want to do the first one? Yeah. It doesn't matter. You're going to have to do both anyway with this, the method that I'm choosing. So you have to integrate this with respect to y, because it has dy. And so this would give you what? Y e to the x plus x sine y. Right? And then also psi is equal to the integral of this one with respect to x. Which is just y e to the x plus x sine y. Which is just a repeat of that, so I just write down in one of those. That's our solution.
I have a question.
Yes.
For exact equations, is it always equal to 0?
You should always be able to write it in this form.
So
Yeah.
it's always equal to 0?
Yeah, you have to have function times dx plus a function times dy equals 0. Yes.
And also for when you like to find an answer, does the term always have to be equal for in terms of x when you integrate?
No. No. You can have very different functions in each of these. You just write down anyone who shows up at least once. You write them down. Yeah.
For the second one, when you took with respect to x, when you took the integral, why is it f of h and not f of y? The constant.
F of, because that's a typo. Yes.
Just in the beginning, I know like it's dy dx, but how did you know where to put the dy and where to put the dx?
Where you mean here?
No, at the beginning. You know how like the y prime is dy dx, and then how did
Yeah.
you find where to put the dy?
Well, I multiply by
dx.
dx. I multiply both sides of the equation by dx.
Stop skipping steps, man. You're confusing your life.
Oh. Okay, so another example. Okay. So can probably write this in a nicer form. What would it be?
Y dx plus
So if I check my and next, what happens? What's next equal? It's not exact. Oh my god! You're like, okay, maybe it's separable. No, it's not. Maybe it's linear. No, it's not, because of the e to the y.
And it's not homogeneous.
It's not homogeneous because of the e to the y. That e to the y just messed up everything. But it's not exact either. What do we do?
Make it exactly.
Make it exact. Remember, mu is our standard variable for an integrating factor. What if I said mu of y equals y here? Multiply through by mu. Right? Multiply through by mu. This would give us, if I multiply this whole equation, what would I get? I would get y squared dx plus 2xy minus y, 2xy minus y squared e to the y. Y, 0. So now, if I check my, what do I get? 2y. If I check next, what do I get? 2y. Suddenly it's exact. Wow. Okay, so this means I can find this function by integrating y squared with respect to x. This means xy squared plus some constant of y. Also, psi is equal to the integral of 2xy minus y squared e to the y with respect to y. That's going to be a longer one. All right, so integrating this with respect to y is easy. In fact, we're just going to get this guy back. What about this guy? How do you do y squared e to the y? How do you integrate that? Right, integration by parts, you're going to have to do it twice. You can also do the tabular method, something like. Also, some of you have learned in talk 2. Differentiate this until you get 0. Keep integrating this until you get to that line. Sign change starts here. Multiply along the diagonals. Y squared e to the y. 2y e to the y. Takes the minus sign. 2e to the y. Takes the positive sign. So the integral of y squared e to the y dy is just y squared e to the y minus 2y e to the y minus plus 2 e to the y. Or you can do
We never
integration
learned
by
this.
parts.
We've never seen this.
Did you guys do calc 2 or not?
Yes, we did, but like, we've never seen this. We'll have to do it the hard way.
Okay. Alright, do integration by parts twice, you'll get to that.
Yeah, we gotta do it the hard way, man.
So now we have that v is equal to xy squared. You guys want to look it up? It's called tabular integration.
If we learned this back in Calc 2, things would have been much easier.
And then minus that guy, so it's minus y squared e to the y plus 2y e to the y minus 2e to the y plus some function of x. And this will give us our solution. Just write down any guy that shows up once, that's this guy. So the solution is actually xy squared e squared e to the y equals 20. And you can check it to the partial this with respect to x, you will actually get that, and to the partial respect to y, you will get that. But notice here, this wasn't exact. I made it exact by using an integrating factor. It turns out here, well, I'm going to tell you a couple situations where you can find the integrating factor pretty easily. But it turns out here for these equations, finding an integrating factor in general is not as easy as it was with a linear equation. There are tons of cases where we don't know how to find an integrating factor for things like these. Right? The mere fact that it's not linear actually gives us a lot more scenarios that we can handle. But there are a few that we sort of know how to handle. In general. It's difficult because you actually need to solve a PDE. Remember, when we're doing linear equations, we needed to solve this separable ODE. In general, for exact equations, you'll need to solve a PDE, and the lowest level PDE course here is a master's level course, and even in that course, solving this is really hard. So, we just won't do it in general, but there are a few cases that actually work out nicely. Yeah, we know 2, 3, or 4. Maybe more. Your book actually goes to like 4 cases that work out nicely. I'm only going to tell you about 2 of them. Suppose we have m dx plus m dy equals 0 is not exact. Right? So suppose we start with something that's not exact, call this equation 2. Then you have these conditions. If it turns out that my minus next over n is purely a function of x. Right. Let's say you do this, you take the minus next, divide by the n, you get a function, but there are only x's in it. Then finding the integrating factor turns out to be easy. Then mu is equal to e to the integral of that function. I'm not going to prove it. There are actually a couple problems in the book that actually walks you through the steps of figuring this out. So if you're interested enough, you can find it, but technically it's not in our syllabus, so I don't want to spend the time on it. I'm just letting you know it's out there. There are cases where you don't have an exact equation, but you can make it like that. And in the case where this works out, this is the guy that will make it. Right? And in the second case, if that is purely a function of y, then you can set mu equals e to the integral of that guy. In these cases, mu makes 2 exact. So for this last example, how did I figure out y was what I needed to multiply? Well, I did this check and I found that this was true. And when you do the integrating factor here, y was the answer. So I just multiplied through that. Yes.
If the top one is true, then that means the bottom is true.
No.
So it's either or?
Yeah, you check one or the other. It's probably possible for both to be true at the same time, but I would think that's a very rare case. So you check one, it doesn't work out. You check the other one, it doesn't work out. Then you can check some other conditions. Your book tells you about these other conditions that you can check for. But if none of them work out, then it's like, whatever. You won't really worry about this on the final, but I just thought it's something you should know about for your general education. I have one type of example to do for section 2.9. I'll probably talk a little bit more about that, but the only thing we'll need for the test is this next one. maybe I have time to. Maybe I have time to do another exact equation and then do that. Sure. All right. I wrote this example down last minute because actually a problem similar to it was assigned for homework for another class, and a bunch of kids came and saw me about it. And a similar question was also on a final one, so I figured I'd let you guys take a shot at it. dx.
That's dx.
Oh.
Oh, I copied that down right.
You guys are killers.
It has to be like a part 2. Question.
No, that's part 1.
Oh, is that part 1?
It's exact equation. All exact equations are in part 1. I told you they're like the easiest ones on the one of the easiest
Yeah,
ones.
that's easier.
It's easy if you see the trick.
Back to,
But the first part is the hardest part, of course. You have to make sure it's exact. So let's check if it's exact. My and next. Partial of this with respect to y. Partial of this with respect to y.
Ow.
What rule do you need? Product rule. E to the xy cosine 2x. xy e to the xy cosine 2x. Remember your calc 2? Well, it's sort of calc 3, but it's really calc 2. And next, this one. Now notice here, you have 3 functions of x.
Question?
Huh?
Is that supposed to be minus
Oh,
x?
wait, we have to finish. What?
Is that supposed to be a minus xy e to the xy?
No, we're not differentiating the cosine. We're differentiating this. I differentiate the y, and then I differentiate this.
Oh, okay.
And then here I'm going to differentiate just the e to the xy.
Oh,
Minus 2x e to the xy sine 2x. This derivative is 0, right? Okay, then we differentiate this one, which you would get e to the xy cosine 2x plus xy e to the xy cosine 2x plus, well, minus 2x e to the xy sine 2x. And they're exact. Right. Here I applied the generalized product rule. Basically, if you have a product of functions, you just have a sum of terms where each function gets to be derivative once. So this is just f prime g h plus f g prime h plus f g h prime. Yeah? I just added all the terms, differentiating one function at a time. So they are exact. So you do that check and you get that. Now the painful part, or not so painful part. Yes.
For the first term e to the xy in my, shouldn't it be like if we treat x as a constant, should it be x? times
No,
e to
in
the
this
xy?
one I'm differentiating the y and leaving this alone. So derivative y is just 1. So now I know my psi is going to be equal to what? The integral of
all of that.
Now there's the obvious brute force way of doing integration by parts twice.
Is that really?
But each of these are revolving integration by parts, so tabular actually won't help you.
Wait.
Crap.
Neither of these functions go to 0. This only works, by the way, when you differentiate one, it goes to 0. It won't work otherwise. Cube differentiate E, it'll never go to 0. Cube differentiate this, it'll never go to 0. It's one of those integration by parts where you eventually get the function back, and you have to move it over the equal sign. Remember those guys? Yeah. So you can do that twice,
Or,
which is the brute force way. Someone who's
Or-
not even thinking about it will
or
just
Or
run
you
into
can plug
that.
it into Wolfram.
Well, we're on the final. We don't have access to Wolfram. Or the more perceptive student can actually tell me the integral of this almost right away. Do you see what that is?
Sine x minus plus equals to 1.
They're both the
screw
same.
it, brute force way.
This is the
Looks
Consider
familiar.
your future class of
Looks
imperceptible
familiar.
It's the product rule. Here is like taking the derivative of e to the xy with respect to x. Here I take the derivative of cosine 2x with respect to x. Right? This guy is actually just the derivative with respect to x of e to the xy cosine 2x. Right? If you can see the product rule happening. Right? So you could see that. If you see it, then your life is easy. You're out of here in like 2 seconds, right? So like, the A+ students would be the ones who get this. Right? So you can sort of tell the people who have the short solution, okay, they're seeing things, they're thinking. Then you have like the A students, B+ students might actually start doing an integration by parts. Let's say we started on this one. It turns out I could, or start int by parts on the first. Let's say you didn't see this. Okay, all right. You might still get an A+ if you get like everything else right. All right, so you would start integration by parts on this one, which would give you what? Let's say I took, so that you can see it easier. Let's say I took the u to be the cosine and the dv to be the y e to the xy dx. Just for example. So then my du would be what? Minus 2 sine 2x, right? What would the v be? Just e to the xy. Right? And so the first integral is going to give me, you know, the u times v. Yes.
Someone said bless you.
Oh, bless you. I thought, okay. All right. The first u times v minus the integral of v du, right? This is a minus 2, so this makes this plus 2.
And you do it.
And then what do you see happens?
Isn't that the same as the one with?
It's the same as the one on this guy. If I had split this into 3 integrals, this one kills that one. And I actually don't have to do any more.
Okay.
Right? So starting integration by parts here, the second term will end up being this integral here with the opposite sign. I get out of integration by parts for free. And then I just have this plus the integral of this with respect to x is just x squared plus a function of y. And then I do it on the other side. And I sort of just want to show you that. I want to show you one example from 2.6. It wasn't really a planned example, so continue on your own. Let me know if you have trouble, and we'll talk about it next time. Maybe. But sometimes, once in a while, a problem like this doesn't show up on every file, but once in a while they might throw something at you to, you know, So especially if like the professor who's writing the final realize he has some like kids that are on point in his class, he just might throw them a curveball. I don't write the final, so I can't tell.
Those are assholes. They are assholes.
But if the guy actually writes the final, decides to throw one in like this, if it looks way too hard, there's probably a trick somewhere. Don't just run. Oh, integration by parts twice. Spend half the exam doing it.
He's seeing that too much kids are doing well.
Yeah,
so he's just
a
like,
few
you know
kids
what?
came to the tutoring center and said, I've been on this for hours, man. I have like 4 pages here. I don't know what's going on. Well, that's just the product rule. Huh? Okay, well, starting to go to our parts here, that cancels what?
What? I spent 4 hours to do it, like 4 minutes?
Because they were trying to do the revolving integration by parts and they kept dropping signs. It was just a mess. Okay, all right. So this one, it has a nice little trick to it, so I thought I'd show you that. Let's do 2.9. We're doing miscellaneous. It's another one of my kryptonite words. Let's forget how to spell miscellaneous.
You're a mathematician, you're not expected to know.
Yeah, but it's still embarrassing. You got me on camera spelling them.
You write your thesis to get your PhD. Well, you gotta know how to
spell check.
You spell check.
Do it on a computer.
But you don't know how to pronounce it when you want to present
Actually,
it, right?
there's no H, there's 2 L's.
See?
Yeah, there you go.
Okay. I'll only do one example here because we'll actually come back to this sort of example. It's basically reduction of order, which we'll do in a more general context somewhere later. But it's just talking about solving equations of the form that is, the y is missing. Right? You have a y double prime and a y prime, but no y. Right? So every once in a while you see examples like this. The method here is called reduction of order. And like I said, we'll come back to this, I think in chapter 3, we'll actually come back to this and do it in a more general context. But for now, let's just do it in this small context. So the trick is to set, it's a substitution, v equals y prime, which would mean v prime is y double prime. This changes it, the equation, to a first order in v, right? So before we had a second order equation, right? We had a second derivative. But if I make this, just call that a variable, then its derivative would actually be that, so it turns into a first derivative equation. So it's a first order derivative. And this is why it's called reduction of order. We actually reduce the order. So we start with a second order equation, we can transform it into a first order equation in which we use any one of the previous methods that I've shown you. So an example of such a question might look like t squared y double prime plus 2ty prime minus 1 equals 0. And assume t is greater than 0. So I look at this, I see, oh, there's a double prime and a prime, but there's no y. So what I can do is I can let v be y prime. This would mean v prime equals y double prime. This would mean I can actually rewrite this equation. T squared v prime plus 2tv minus 1 equals 0. And now it's a first order equation. So we can use one of the other techniques on it. What kind of equation is this?
Is it linear?
It's linear. Right? Yeah, do you have another question?
No, I was going to say you add 1 to both sides, find the integrating factor.
Yeah, you add 1 to both sides, and you'd have to divide by t squared, put it in standard form.
Oh, yeah.
Right, so this is t squared plus 2tv equals 1. Divide through by t squared. It's not 0, so we can divide by it. V prime plus 2 over t squared, 2 over t v equals 1 over t squared. So our integrating factor is e to the integral of 2 over t dt, which is e to the 2 ln t, which is just t squared. So I multiply this through. Oh, it was already in the form. Oh, that was nice. Just wasted time. Yeah. I'm not an A+ student.
And you expect
Totally
us to be an A+
Okay,
student,
so-
right?
I mean, we wasted 5 seconds. All right. Routine. Okay, so we pretty much come back to where we were before. The left side was already the product rule. And so this is just t squared times v all prime is equal to 1. Integrate both sides. This gives us t squared v is equal to t plus c. This means that v is equal to 1 over t plus c t to the minus 2. Right? This means,
And the last line, is it supposed to be a B or 2T?
no, this is the product rule. It's the mu times the v all prime. Right? Mu was t squared.
So then v prime has to be.
But v was what? Y prime. So this means y prime was equal to 1 plus t plus c t to the minus 2. Which means now I can actually just find the y by integrating with respect to t. Right? So I integrate this with respect to t. Where do I get?
ln t.
ln t. Technically it's absolute value t, but t is positive, so I can drop that if I want. Minus plus a constant, but we usually don't care. Plus some other constant.
d.
So it's just a nice little trick. If you see a double prime and a prime, you can just replace this one. And it can work more generally, so we'll stop there for now. I'll probably mention a little bit more about chapter 2 on Monday, and then we can talk about the review problems and any questions you have on the homework and so on and so forth. So now we have quizzes!
Really? We have a class.
I'm kidding, to get back to quizzes.
Oh. I was